mistake, no?
0, it is a square, a square is comma 0.
Yes,
When it's 1 comma
yes,
0, it will be minus 1 minus a square comma 0. This
right.
sign square.
Mm-hmm.
It will form a triangle
Yes,
here alpha. We will get a perpendicular and with respect to this, it will be a cos alpha a sin alpha this point, and this length is b. That means it will be a cos alpha plus beta plus b comma a sin alpha this point,
yes, yes.
and rest is this point. We can form a triangle here,
Right.
and we have this is midpoint is one half,
Uh-huh.
and we have
Some relation between A
yes,
and B?
we have this length, total length, this is
Yes,
a sin alpha
yes, yeah.
minus this length we can find, this is a square sin, as this is angle is pi,
Mm-hmm.
it will be pi minus alpha, and it is midpoint square
Yes.
of pi minus alpha by 2, this angle,
Mm-hmm.
and sine of pi minus alpha by 2 into a square will be x, and this minus this point is
Yes,
we have all the points parameters.
but you see there are two equations, yes? So everything depends only on one parameter.
Yeah, everything is depend upon a for now.
You expressed everything
It
in
is a, it is in a, it is in a, it is in a, everything is.
everything depends on A.
A, and here only this, in this place we have used beta b there, this point, or rest all is upon a and alpha.
No, B is also expressed in terms of A.
Okay,
B is expressed in terms of A, and alpha is also. Everything depends on
as
one.
we can find it, it is a square and we have to find this value, then
Mm.
we can verify it.
If you make this right angle, then it will be
It
good.
will be basically square or rectangle. Let
Oh
me check.
no, you cannot make a right angle here because this.
Obviously this will be anything anywhere else, this point will
Mm-hmm,
be somewhere else we can
mm-hmm,
see.
mm-hmm. Yes, I don't know how to solve these equations. I forgot because I made it, but now I forgot how to solve them. Okay. Okay, so you finished the job, yes? So I don't remember how to find the parameters for this. Or maybe we can just or maybe alpha let alpha be 2 pi divided pi divided by 3. No? What angle is it good?
I have removed that b.
Yes?
I have removed that b. This large triangle, there will be alpha, and
Yes?
this length will be
Yes.
hypotenuse into cos alpha,
Yes,
and
yes.
1 minus that much will be b is
Okay.
removed.
Okay, so please construct it. So if you manage the parameters, then construct it.
So I have to just what we have to do? We have to just translate, or
So
what we have to do?
so there are two maps. Hmm. Let me check because I had this Hata double somewhere in my records, and it will be more easy to find it. I cannot remember. Hata double. Maybe it is here. Oh, I have it, yes. I have it. This double. Okay. Do you see the picture? Rendering. Background. View palette. Okay. Okay, see. So now it's visible, right? I did it long ago. You see, it is possible to construct it, but I don't remember how to make this hot double D0 DI main tree. Oh, we have, you see, but I forgot how to construct a formula. Maybe I will find it. Oh, where is editor? I look to editor and source. Hey. Oh, it is a problem to find it. Okay. At that moment, I cannot remember how I computed these numbers, but they are in the program, and I will look at it and then explain. I wish you to make one more experiment. One more experiment, and then we'll proceed to other things. Take the equilateral triangle. Yes. Make here two smaller triangles, and make here two such triangles. You see? So we'll make a self-affine dendrite. So this map will send. Oh, let us excuse me. Let us make it the following way. I take a equilateral triangle and make this two copies less than one half. So it will be some number, maybe 0.4. Then I have 0.6, yes, and I add two affine mappings. These affine mappings will send this triangle to this one. And this affine mapping will send this triangle to this one. Okay. This vertex is preserved. So let us look what happens if we construct a self-affine system. So if it's 0.4, this will be 0.6, this will be 0.6. Yes. Since this system is symmetric, we can use the symmetry with respect to this bisector. Yes. So we just write these two maps and then make a reflection with respect to line which goes at the 30 degrees angle. Okay, so but we need to have this triangle, these two triangles, they must be, this height of this triangle will be such that it doesn't touch this this bisector. Okay. So what we have to do? We have two maps. This map will be 0.4. This map will be 0.4. First, it will be translation by 0.60 multiplied by contraction with the ratio of 0.4, right? And this map, so you need this parameter h, it must be, so h divided by 0.3 must be less than this. This is 1 divided by square root of 3, right? Because the tangent of pi divided by 6 is 1 divided by square root of 3, right? So h is less than 0.3 divided by square root of 3. So if you take this h, and now you construct a map which sends this triangle to this triangle. So it will, the y-axis has a contraction h divided by 2h divided by square root of 3. Yes? And the x-axis has the contraction 0.6. Therefore, this map will be written in the form S1 of S1 will be equal to matrix 0.6, 0, 0, and the value of 2h divided by square root of 3. Yes? So you need to compute this h. Compute this h so that, and S2 will be more, have more humane form. It will be 0.60 multiplied by 0.4. Yes? But we have not 2 maps, but we have 4 maps. So we need to have a reflection with respect to this diagonal. Yes. Maybe it is better to do in slightly different manner. Okay. So how to reflect? How to write a reflection? So we have a line with which which has angle A with x-axis, yes? And what is the reflection with respect to this line? How to draw a reflection with respect to this line? So if you have a point xy, yes, you have a point xy, it is reflected to this point. For example, xy are cosinus alpha, cosinus cosine phi r sine phi, it goes to, and this is alpha, this will be r. So if you, this is r e to the power of phi, if this angle is phi, then this angle will be, you have alpha and phi, and this angle is alpha minus phi, right? This angle is also alpha minus phi, so you take this angle will be 2 alpha minus phi, 2 alpha minus phi, right? So if you have r cosine phi r sine phi, it goes to r cosine alpha minus phi 2 alpha minus phi r sine 2 alpha minus phi. Yes, these computations are too not convenient for us, so let us make the example more simple. We take a right triangle. You have two such maps, and you also have two maps which send this triangle, for example, to such one. You have a map which sends this triangle to this one, and then you have a reflection in this diagonal. So can we write this map? Sorry, I am a little exhausted and my examples are not good. My examples are not good. And what? Yes, I have a, tuition till 5:30. It's okay. So let me continue talking about open set condition, which I didn't finish in the morning, and I will can explain it using my notes. So suppose the system S satisfies the open set condition, and we considered that index space or address space, and we so we have the system S, S1, Sm, and the coefficients are Q1, Qm. So we found the similarity dimension, which is the solution of this equation, yes? And for this similarity dimension, we introduced a natural measure on I infinity, which is defined by an equation mu of I1 Im I infinity is equal to Qi1 Im n to the power of s. So this was a natural probability measure on I infinity, which sums up to 1, so it is probability measure. And now we consider the measure mu waved on K, such that mu waved of A is equal to mu of pi minus 1 of A. So it will be the projection of the measure mu. So we have the space I infinity. We have a projection of I infinity to K. Yes. Here you have the measure mu. Yes, which is natural, and its projection will be mu waved. It is also called the natural measure on Q. Natural measure on Q. Let O be the open set. Pen set. Of course, we take this open set is bounded. So we have union of Si of O belongs to O. Yes, and if we take closure, it is the same. And therefore, K is a subset of the closure of O. So if we take this open set, then the attractor will be contained in the closure of the open set. Consider the family. Oh, no. Take take some ball BR contained in K, so we consider just the intersection of this ball. Yes, some ball BR. So we can consider K as the whole space, but no, let us take some ball BR such that BR intersection on K is not empty. Yes. So we have a self-similar set, and for this self-similar set we take a point and take a ball and consider the portion of this self-similar set which is contained in this ball. We'll evaluate. It's fantastic. Yes, we'll evaluate this natural measure of BR. We'll evaluate the natural measure of BR. How can we do this? We'll do the following thing, which was initially performed in Hutchinson's paper, and then it was a standard way of considering this problem. So we take a ball BR, and consider all copies of K which intersect BR and at the same time have approximately the same size as BR. So inside K we consider only those copies which are whose diameter is less than BR or maybe less than BR but not very much. As I remember, so I will consider such family. Let QR be the family of such tuples or multi-indices. So each multi-index is I1, Ik for some K, and they are formed in such way that Qi1 Ik is less or equal than R, and Qi1 Ik minus 1 is greater than R. So we consider the set, we can think that the diameter of K is 1. So not to make our computations more complex, yes, we think that diameter of K is 1. We can do this just applying some similarity to the whole space so that our attractor is good. So what will be QR? So we have this ball and we consider the copies whose diameter is smaller than diameter of the ball, but the previous copies for them are greater than this ball, yes? So the immediate consequence of this inequality will be the following, that R is greater or equal than QI1IK, and at the same time QI1IK will be greater than R multiplied by Q minimal. You see what I have done? I multiplied this by QIK, then I have this if I multiplied this by QIK, then R is multiplied by QIK, but R multiplied by QIK is greater than RQ minimal. Okay. And I will write this inequality here because I will use it. You see that R is greater than QI1IK, IK, and more than RQ minimal. This family QR, we already discussed this family, yes? Because all the elements of QR are incomparable, yes? And if we take the union, if we take all Si of O, if I take such Si of O that belongs to QR, then this set will not intersect each other, yes? Because if we have an open set, and if we have two incomparable multi-indices, then the images of respective similarities of the open set with respect to these similarities will not intersect each other. First, do not intersect. But at the same time, this family is full in a sense that the union of Si of O closed, where I is in QR contains K. The images of the closure of the open set will cover the whole K, right? Do you remember, I already told something about that. You see, for any point in K, there is at least one multi-index, I1, IK, such that this point is contained in a copy with this multi-index, yes? So, therefore, but each copy, but Si1 Ik of K is contained in Si1 Ik of the closure of O, because K is contained in the closure of O. Therefore, this union contains the whole K. Very good family, because it consists of the images of O, which cover the whole K, and they are approximately of the same size, and their interiors do not intersect each other. So we very strange self-similar set. Its copy could intersect and so act themselves in very different ways. But when we take this open set condition, it makes them conduct uniformly. So this is what we have done. But let us return to the ball BR, for whose measure we're supposed to evaluate. We have the ball BR, yes? And all these multi-indices were arranged in such a way that the images of K, the sizes of the images of K under these maps are commensurable with the, are approximately the same size as this ball BR. Therefore, in the set QR, we will take a special subset. So I don't remember what notation I used. It will be Q1. Let Q1 be the set of such multi-indices in QR such that SI of the closure of O intersects BR. Now we have the following picture. Instead of copies, we have the images of open set. The copies can intersect each other, right? But open sets are disjoint in the family QR. So we have the ball BR, and we have these copies corresponding to the family Q1. They are of approximately the same size as BR, yes, and all they intersect BR, but at the same time their interiors do not intersect. And if you have a family of approximately equal open sets which do not intersect, and we take some larger ball, then the number of this set can be evaluated, yes, because they are of the same size, do not intersect, and their volumes add up to the volume of the ball B. But we don't need very exact evaluation, we just need some number, because we're supposed to use the mass distribution principle. We need some constant. In mass distribution principle, we write mu of A or mu of BR less than C R to the power of S. No matter how great is the constant, it was enough to have some constant, yes? If we have some constant, then we are done. Okay. So, can you see this part of the blackboard? It was in a sleep mode. I don't know. Do you need this part which is written? Can I erase it? So everyone allows me to erase it. Okay. The open set O is bounded. Yes? So if we have a bounded open set, then and take some point in it, then we can draw a ball in which the open set is contained, and this ball will have radius R2. Yes? And also for this point we can draw a ball which is contained in this open set, and it will have radius R1. Or maybe A2 and A1 because R is used. And this is the open set O. Now we consider these open sets which are arranged around this BR. We have a family of open sets who are friendly to each other and do not intersect. They do not intersect. You see, each of these sets is contained in a ball, like that, and each of them contains a small ball, like that. Yes, and the diameters of these balls can be evaluated. So how to evaluate the diameters of these balls? This set is Si1 In of O. And Si1 In of O has the coefficient Qi1 In. And Qi1 In satisfies this inequality. You see this inequality? It is less than R and more than R multiplied by Q minimal. Okay. So diameter of Si1 In of O, I1 of O, Si1 In of O is contained in a ball. Si1 In of, you see, we took this open set, we took a point in it, and we have drawn two balls. One of radius R2 and the other was of radius R1. Yes? So it will be maybe, I will call it B2 and B1. If you won't object, I will call this by these two nice names. Yes, so Si1 In of is contained in Si1 of In of B2. B2. And the diameter of Si1 In of B2 will be less or equal to Qi1 In multiplied by 2R2. Yes? Qi1, but Qi1 In is less or equal than R. So it will be less than, or it is not R2, it's A2, because I know that I could have some inconvenience using R. So it will be Qi1 In multiplied by 2A2, and it will be less or equal than 2RA2. Okay, so all these balls have the size, have the radius less than RA2. So we have a picture. You have a large ball, and here are balls, and their size is 2RA2. 2RA2. And this diameter, 2RA2. And this radius is R. So all this picture is contained in the large ball, very large ball, which has the radius R multiplied by 1 plus 2A2. A2. So these are the large balls containing these sets I1, In of O, which intersect this ball. But for each ball there is an open set which also intersects R, and it contains a small ball. Yes? And the radius of this ball will be greater or equal than RQ minimal multiplied by A1. RQ minimal multiplied by L1. So this radii will be greater of greater or equal than R Q minimal multiplied by A1. So now we need to count how many balls of this radius can be contained in a large ball of this radius. It will be R multiplied by 1 plus 2A2 divided by R multiplied by Q minimal multiplied by A1, and all this will be to the power of n when n is the dimension of the space. Yes? Because a circle, if we divide the circle to disk, areas of the disk, then we have squares. If we have balls in 3 dimensions, we have cubes. In an n-dimensional space, we need to obey the laws of n-dimensional space, but R about which we had our concern. We were concerned with the ball of radius R. By some happy coincidence, this R is cancelled. So this evaluation doesn't depend on R. So whatever ball we take, and if we consider the neighbors of this ball, yes, neighbors of this ball, the number of neighbors will be always less than this number, and it will be C. Therefore, the measure of this ball is the measure of its intersection with the copies. The copies which contained in these closed sets. And the measure of each copy will be I1 In multiplied to the power of S. Right? I1 In to the power of S. But I1 In is less or equal than R. So the measure of each copy will be less or equal than R to the power of S. Therefore, we have that measure of BR is less than equal than C multiplied by R to the power of S. We are done. We are done. Yes. We can apply it mass distribution principle. And from mass distribution principle, it follows that Hausdorff of dimension of K is greater or equal than S. But at our first stage, we proved the opposite inequality. Therefore, it is exactly equal to S. So, and this Hausdorff dimension is equal to box dimension and to similarity dimension, because similarity dimension is S. So now we finished this theorem, and we can make some. We have 1 more hour, but maybe we'll make a 5 minutes break at least. So this proof is very basic. What we say? And it looks nice. If to pronounce it slowly. But if to pronounce it in fast words, it looks ugly. But what is interesting, from this open set condition, we also have one very interesting consequence, that each copy has a finite number of neighbors which can intersect. So, if we take some ball, then the number of copies which can intersect this ball is, it depends on the radius of the ball, yes, and it is bounded, no matter how far we go. So this is very good regularity property. For example, if we have a self-similar dendrite which satisfies open set condition in space of any dimension, this dendrite can have only finite number of branches. It cannot be infinitely ramified, because each branch corresponds to some copy, and the number of copies is bounded from above. the self-simul in draft. It is made of such a polygon. And inside this polygon we have one copy, second copy, third copy, fourth copy, and also we have 1, 2, 3, 4, 5, 6, 7, 11 copies. But due to the organization of this copy, this dendrite, this point has an order 3, because there are 3 branches. If we delete this point, these 3 branches split apart. Yes. So, at this point, we have 33 branches. The unification order of this point is 33. I will enlarge this picture. Sorry, let me picture it. So we have a point of order 33 because there are 33 branches. This angle is 30 degrees. I cannot make 12 angles. They will glue together. But here we have 33 connected components if we delete this central point. And this is the main, main tree is, yes, this is, main tree is here. The main tree is very simple. This are 3 out, 1 out goes to this point, 1 out goes to this, and 1 to this. But if we make a first image of the main tree, then we'll get this picture. And if we make a second iteration, then we'll find. Do you see this picture? Is it visible? Oh, yes, it is visible. Oh, quite well.
Please near the mic. Voice is not recording.
What?
Please near the mic.
Oh, yes. Okay, so we proved the open sync condition, and now we can proceed further to some other things. So in case when open set condition is satisfied, the Hausdorff dimension can be found easily. It is just the similarity dimension, yes? But we can imagine this case when the similarity, when the open set condition is not satisfied, but nevertheless we can find the Hausdorff dimension of the set. For example, consider this the following triangle. I will draw you one triangle. So let Q be the golden mean. Q squared plus Q equals 1. And I take the following thing. Yes, I will take, this will be Q, this will be Q, and this will be Q squared, right? So this copy will intersect. It is easy to construct this golden triangle, yes? And if you look at it, then since this is a Q, and this is also Q, then 2Q plus 2Q minus 1, Q minus 1. You see 1 minus Q, Q squared is equals 1 minus Q, right? Therefore, 2Q minus 1 is equal to Q minus 1 minus Q, right? It means that it is Q minus 1 minus Q minus Q squared, but Q minus Q squared is Q cubed, right? So it is, if it is K, if the whole triangle is K, this will be K1, this will be K2, this will be K3, say, and this will be K, K1, 2, 2, and at the same time it will be K2, 1, 1. Do you know the golden mean? It's square root of 5 minus 1 divided by 2, right? Okay. So you write Q equal to square root of 5 minus 1 divided by 2. Can you be so kind to build this fractal? Please. Please. Show your kindness. Can? It's easy. Very easy. So there are only 3 copies. This number can be calculated because IFSTile can make such algebraic calculations. So with I think 15 digits after the comma. It's sufficient to make the mistakes invisible. They are very, very small. Okay, so can you do me a favor and construct this fractal? it looks very nice. Thank you. Do you understand what kind of maps this is? So first you need to define this Q. Then you made Q squared, then you have a translation by 1 minus Q. It is translation by Q squared too, right? 1 minus Q is Q squared. So you have Q multiplied by K, and you also have Q multiplied by K translated by Q squared. And also you have Q multiplied by Q squared translated by Q divided by 2 and by X, and Q square root of 3 divided by 2 by Y. Okay? So there will be 3 maps, S1, S2, and S3. Yes?
In second last, how Q3 can?
K3?
Q3, Q cube.
What?
Second last.
Q cube. Q cube. This is the intersection. The intersection is a copy of order 3. Yes. And when it is constructed, it is very well visible. Okay? Can you build this one? Oh, but this will be q squared. Of course, this is good that you have such an overlap, but let it be q squared. So maybe, oh yes, q squared. This translation is I made the wrong translation, yes? I, the, the coordinate of this point, what it is the coordinate? This is q, yes? And this point is q square root of 3 divided by 2, right? Yes? Oh, no. Q square root of 3 divided by 2, it's vertical. And q by 2 and q square root of 3 divided by 2. This is that point, yes? So this operator will be uh, q by 2 q square root of 3 divided by 2 multiplied by q squared. Yes, okay? And in this case, we'll have an equilateral triangle, but if we change the coefficient, it will grow higher. Yes. This is a very nice picture. But I constructed it something maybe in 203 or 204, and I cannot recover it. So I have just an image. I don't know how it was obtained. If you succeed in building it, I will be very happy because I have on the GPG. I have only GPG file, yes. Because when Dmitry Mikhontsev made the IFSTile, then all PNG images which are saved by this IFSTile program contain the IFSTile code. It's very good. this is not the one. And this is a self-similar three-dimensional tile. Usually tiles are balls, but this tile is torus. This torus is composed of smaller copies of this torus. It was invented, so this IFSTile has the search machine. And Mikhontsev was always searching different fractals, especially tiles. So he's a person who has seen more fractals in his life than anyone else, because he saw thousands of them. Yes, and among them he found such unique examples that different figures can tile the space, but to tile the space with tori and also so we have this figure, yes, and then we add the same figure, yes, of the same size. Then we add one more figure and one more figure of the same size and one more and one more, one more, one more. So did you make this golden triangle? Because I need to see your results, and then I will explain how to find its dimension. Because uh, This golden triangle doesn't satisfy open set condition because it's his two copies of first order intersect in a copy of third order, yes? But it's an exact overlap, yes? Therefore, we can write, so measure of its, you say, q to the power of s plus q to the power of s plus q to the power of 2s and minus q to the power of 3s should be 1. And this will be the equation for the similarity dimension, which takes into account the exact overlap. So if you may take some program, mathematical, which solves such equations, cubic equations, yes, you will find S, right? You will find this, and then you can compare this S with the dimension which you obtain in your program.
But how can we mathematically say it's the dimension will be same? Similarity, basically S will be the dimension of
It's just counting of measure. Measure of this set plus measure of this set plus measure of this set will be measure of this set plus measure of this set. So I add two measures, three measures, and then I subtract this one. And all this will give us 1. So it's quite simple. Yes. So very good equation if you have Wolfram Mathematica or some Maple or whatever like MATLAB, you can find the solution, take logarithm with respect to q and get the same result which is shown here in But if you wish, you can also, this is not good, this is not a dendrite, but we can make a dendrite with overlap, yes? You see, if I take a cube and take copies in this cube, this will be 1, 3, 4, I must count these numbers. So it is, if it is q squared, it will be good. Q plus 2q squared, q squared is equal to 1 plus q squared. 1 plus q squared. Q plus 2q squared is 1 plus 2q squared. No, I don't remember. We need to find some other number. Q. If I take this will be q, this will be q, then this will be q cubed. Okay, q cubed. Q. I don't remember, so but we have such a dendrite which has an exact overlap. No, we need not make it. So if it is A and this is B, and this is B, then it should be, or maybe we can make it a different way. To make computation more easy, we can make it the following way. Um, oh no, we cannot do this way. I don't remember how to make it a dendrite. Of course, there is a way to make a dendrite this following way. Yes, if we make here one triangle and one triangle here, then it will be okay. Yes, so it is q, this is q squared divided by 2, this is q squared divided by 2, and this is also q, and this is q cubed. Okay, then we'll have a dendrite with overlaps, but also we can make dendrites with overlaps with cubes. So did you finish? Yes? Yes, 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 okay. Yes, you're right. We have 10 minutes left. Yes?
So how we are writing its ratio is 2q minus 1.
Oh, I wrote the computation. Please, I will repeat it. I will repeat it. It's very simple. So, you see, 2q minus 1 is equal to q minus 1 minus q, right? So it is equal to q minus q squared, right? So it's q multiplied by 1 minus q, but 1 minus q is q squared. What?
Why we are taking 2q minus 1?
2q minus 1. You see, this is q, and this is also q. So the overlap is 2q minus 1. You have 2q, but they are on the interval of the length 1. So their overlap will be 2q minus 1. Yes. So this golden mean is very interesting number, yes? Hmm?
Golden ratio. Golden ratio.
What?
Under root 5 minus 1 by 2 golden ratio, no?
Yes, yes, yes. But if you wish to enjoy a little, you can also construct such a zipper. One, 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 one. Yes. It has 1, 2, 3, 4, 5, 6, 7 copies. This will be 0, this will be 1, this will be 2, this will be 3, this will be... You see, the signature is 0011100. Yes. And it will give very interesting result. When I saw this result many years ago, I understood nothing, but it was surprising for me. Yes. What? Yes, of course. You see, you have 6 minutes. That's enough to build this picture. Hello, hello, hello.